In particular for today's session, we are very lucky to have an international expert, Philip Hibbs, who will share his experience with us today. The sharing session for today theme is the hazard in the construction industry with a focus on the RCS or respirable crystalline silica. Before we start, I would like to read his biographical notes. Philip is an occupational hygienist with more than 35 years experience. He has worked as a consultant for most of his career, providing advice in the construction, manufacturing, and maritime industry on hazards related to asbestos, dust, and chemical, confined spaces, heat stress, height safety, and indoor air quality. He established HIBBS and Associates Pty Ltd in 1994. So it's long ago, yeah.
Nice.
94 is the year I entered my college. So he holds a Bachelor of Science from the University of Melbourne and a graduate diploma of occupational hygiene from Deakin University. Philip is also a fellow of the Australian Institute of Occupational Hygienists and was its president in 2017. He is a certified occupational hygienist or COH. He is currently the chairman of the Faculty of Asbestos Management of Australia and New Zealand, and he's also board member of the Australian Institute of Occupational Hygienists Foundation. He's also the chairman of the IIHA National Accreditation Recognition Committee, or NAR, and board member of the Asian Network of Occupational Hygiene. So I can assure you he is a very busy man. He also member of many industrial hygiene society, for example, Indonesian IIHA Association. So Philips is actually the IIHA international member. And also he is also member of MIIHA and New Zealand Occupational Health Society, accredited with the Health and Safety Association of New Zealand. He also the member of BOHS, British Occupational Hygiene Society, and American Industrial Hygiene Association, American Conference of Governmental Industrial Hygienists, NATA Chemical Testing Accreditation Advisory Committee, Standards Australia Technical Committee CHO31 for methods for examination of workplace atmospheres, Certified Professional Member, Australian Institute of Health and Safety, Australian Land and Groundwater Association, and Clean Air Society of Australia and New Zealand. So I'm sure this only a brief summary of wide experience. So without further ado, okay. Before we start the presentation, I would like to remind all the participants to mute the microphone. Okay. So during the presentation, please mute your microphone. We will have about 45 presentations, and then we will open Q&A session. During the presentation, if you have any question, you can type in the meeting chat. And in the Q&A session, if you want to raise any question, please click the raise your hand icon so I can give your time to give the question to Phil. Okay? Okay, without further ado, I will let Phil to start the presentation.
Okay, and thank you, Elsha. When I've got my screen share running and the presentation up, I can't see any typed questions, or when people raise their hand, say, "Oh, sure, if somebody's got a question they want to ask, can you stop me?" And then we can address it during the course, or it can wait until the end if it's not urgent. Okay.
Okay.
Before we get going today, I'd like to take the opportunity to thank the Indonesian Industrial Hygiene Association for the invitation to speak to you on what's a really quite an important topic and a very topical occupational health and safety issue at the moment. Now, the presentation, we actually had to change the title of the presentation and what we were going to talk about earlier this week, and I relied on my colleague Linda Apthorpe to assist me with putting the presentation together. So quite a lot of the slides are a mixture of hers and mine. So before we, what I'd like to talk about today, and bearing in mind that I will forward a copy of the presentation to everybody for distribution. And to be quite honest with you, it's not actually been completely finalised because I was still fiddling with it 20 minutes ago when Mila contacted me and said, "We're starting in 20 minutes. And I thought we were starting in 2 hours and 20 minutes. Anyway, so I thought what I'd like to talk about is construction industry hazards, so that's dusts in particular, respirable crystalline silica, diesel particulate matter. I had intended to talk a little bit about welding fume, but I didn't end up putting those slides in. Asbestos is a topical issue, so we'll spend a little bit of time on that. But the other hazards that are present are noise, heat stress, chemicals, falls from heights and falling objects. But we won't talk about the last three, and I haven't included any slides on welding fume, but we can talk a little bit about that separately if you want. So what does the construction industry include? Well, generally we think of building things, standalone houses, residential apartment blocks, commercial buildings, things like multi-storey high-rise blocks, hospitals and schools, or warehousing, or maybe industrial complexes, infrastructure developments, so that's roads and rail networks, bridges and the like. However, increasingly in our developed cities, before new construction projects can commence, older existing structures have to be demolished. Now, the demolition of older and existing structures has a range of unique occupational hygiene issues to be managed. Now, we won't consider safety aspects of demolition, such as, sort of unplanned building collapse or falls or falling objects, but those aspects of the demolition process injurious to worker health. So things like to be considered would be hazardous building materials, so asbestos-containing materials, we'll come back to that later, synthetic or man-made mineral fibre products, electrical components containing classes of compounds such as PCBs, and they're present in light fittings and transformers. There's lead-containing materials, coating systems and paints that contain heavy metal compounds used as dryers or pigments, things like chromium and lead. There are pesticide and arsenic compounds used for termite treatment, chemical compounds from past industrial processes that may have been conducted in the building, ozone depleting substances such as chlorofluorocarbons and mercury compounds. Radioactive sources, including things like smoke alarms and exit signs, and there are biological hazards to manage, including mould, fungi, bacteria, Legionella and guano, and most significantly, particulate matter or dusts that have accumulated inside the building in hidden areas intimately sealed within the building structure, or that can be generated during the demolition process. Now, these dusts can contain metals, pesticides, asbestos, but very often they contain respirable crystalline silica. Now, after previous structures have been demolished, there is often site preparation works to remediate contaminated land, which have contaminants from a wide range of hazardous chemicals, the most common of which we would encounter would be petroleum products from underground storage tanks. But site remediation works has its own occupational hygiene hazards, and it's outside the scope of what we want to talk about today. Now, the initial stages of construction involve site preparation works and excavation of land for basements and piles to support larger buildings and overhead structures as our cities reach skyward. Excavation works can generate dusts, often again high in respirable crystalline silica. Now, I mentioned infrastructure development. Increasingly, in our larger cities, where open land is scarce and there is a rise in the demand for transport, we are putting our road and rail systems through networks of underground tunnels. There are several such projects currently underway in both Melbourne and Sydney in Australia, and both the Melbourne and Sydney are underlain by geological strata that's high in crystalline silica. So the sorts of hazards that we might encounter are summarised on this slide. We haven't listed them all, it's certainly not exhaustive, but today we'll be focusing on just a few of these. The big one for Australia at the moment is respirable crystalline silica, and that's due to the large number of infrastructure projects currently occurring across the country, and also as a result of the very unfortunate story of stonemasons working on engineered stone. We have an engineered stone industry here. It's been very poorly controlled, and as a result of that, there's been very significant exposures to respirable crystalline silica that have resulted in acute silicosis and the deaths of many workers. Now, silica or silicon dioxide is a naturally occurring and widely abundant mineral that forms the major component of most rocks and soils. It's one of the most abundant minerals in the Earth's crust. Now, crystalline quartz is the basic component of soil, sand, granite, and many other minerals. And quartz is the most common form of crystalline silica. It is very commonly used in industry and is present in a wide variety of common building materials. Uncontrolled cutting, grinding or drilling of products or materials that contain crystalline silica can generate high levels of airborne dust containing respirable crystalline silica. Long-term exposure to respirable crystalline silica at levels exceeding the workplace exposure standard presents a serious risk to health. Now, silica is also present in two forms. It comes as a crystalline form and an amorphous form. Now, amorphous and crystalline are two states that describe typical solids in chemistry. Solids, hang on, excuse me. Solids are among the three basic states of matter that include also liquids and gases. Now, solids are characterised by a rigid structure of molecules or ions and atoms that can be arranged in either an ordered or a random, i.e. non-ordered manner. Now, the ordered or random arrangements have led to the categorisation of amorphous and crystalline. In crystalline solids, the atoms are arranged in an ordered three-dimensional network lattice of uniform intermolecular forces. The atoms are intersected at angles that are characteristic of the crystal, and they are symmetric, they are isometric, and they have clear, defined melting points. So this is here to try and represent an ordered array, regular pattern of atoms in a crystal. Now, and that's your crystal there. Now, a typical crystal you might think of as diamond. That is a network crystal lattice structure. Now, on the other hand, amorphous essentially means shapeless. Amorphous solids do not have a defined geometric shape. That is, the arrangement of the atoms is random or irregular, as I've shown you here. There is no regular pattern to that arrangement of atoms. The intermolecular forces are not equal, and the distance between the atoms or the particles varies. They're generally they are isotropic and do not have generally don't have a well-defined melting point. And they're also often referred to as supercooled liquids. And the typical amorphous material is glass, common soda glass, like my drinking cup. Now, crystalline materials can exist in more than one polymorph. Crystal polymorphs essentially have an identical chemical composition, but exist in more than one crystal form. And different polymorphs have different internal crystal structures, and they can also have different properties, and they exist in different physical conditions. Crystalline silica has three polymorphs. We've got alpha quartz, cristobalite, and tridymite. The most common form of silica found in construction sites will be quartz. It's present in soils and rocks, and in building materials including concrete, sand, cement, bricks, and ceramic tiles. In construction, the most common form of crystalline silica is quartz, and it's most unlikely that you will encounter either cristobalite or tridymite. Now, cristobalite can be found where amorphous forms of silica have been calcined at high temperatures, generally exceeding 1,000 degrees C, and the silica is then converted into cristobalite. And cristobalite is also present in engineered stone. So that's the type of stone that I was talking about previously. Tridymite can also be formed at very high temperatures, but usually at low pressures and as a byproduct of some chemical processes. I doubt that you will ever encounter it in construction materials. Now, the photograph here is an interesting one. It's a Herkimer diamond, which is a double-terminated clear quartz crystal. Now, they're called diamonds due to their high clarity and their natural faceting, but it's not carbon. It's not diamond, which is actually a carbon network lattice. Now, all the polymorphs of crystalline silica are classified by the International Agency for Research on Cancer, that's IARC, as Group 1 carcinogens. So, respirable crystalline silica is an inhalation hazard. Inhaled particulate matter that evades interception in the nasal passageway will find its way into the respiratory tract. Particles inhaled into the respiratory tract closely follow movement of the air in which they are suspended. The behaviour and deposition of these inhaled particles in lung airways is related to their physical characteristics, so that's the size, the density, the shape, and the aerodynamic properties or aerodynamic diameter, but as well as the volume and the rate of respiration. So that airborne particles of silica in the respirable size range can be inhaled, transported and deposited into the alveolar regions. And exposure to respirable crystalline silica can result in chronic bronchitis, emphysema, silicosis, lung damage, and also in scleroderma, which is a disease of the connective tissue of the body. We'll come back to exposure standards shortly. So silicosis, I'm just wondering if I'm on the right side. Yes, I'm definitely on the right side. Silicosis is classified into 3 types. So you could get chronic or classic silicosis, accelerated silicosis, or acute silicosis. Now, chronic or classic silicosis occurs following long-term exposure to relatively low levels of respirable crystalline silica. The symptoms associated with chronic silicosis may or may not be obvious, and therefore workers need to have a chest X-ray to determine if there is or has been lung damage. As the disease progresses, however, the worker may experience shortness of breath upon exertion and then end up with the clinical signs of poor oxygen CO2 exchange in the latter stages. As the worker, in the latter stages, the worker may experience fatigue, shortness of breath, chest pain, and ultimately respiratory failure. Accelerated silicosis occurs after 5 to 10 years of moderate to high exposure to respirable crystalline silica. Symptoms include shortness of breath, weakness, and weight loss. Now, the onset of symptoms takes longer than acute silicosis. Acute silicosis occurs after a few months up to 2 years following exposures to very high concentration or extremely high concentrations of respirable crystalline silica. The symptoms of acute silicosis include severe disabling shortness of breath, weakness, and weight loss, and it often leads to premature death. Now, the one thing to note about silicosis is that it continues to progress after workplace exposures have ceased. This photograph shows a cloud of dust at a concrete recycling or concrete crushing and recycling plant in Sydney. Now, what is the particle size distribution in the dust cloud? Now, the visible particles that you can see are greater than 100 microns in diameter. They fall out of the cloud quickly and are too big to be inhaled. Particles that are less than 100 microns in this size range can be inhaled into the respiratory system and are called inhalable particles. Then the last fraction of this dust cloud are the particles that are less than 10 microns. And particles in this size range can be inhaled. They're referred to as respirable particles, and they can travel down to the alveolar regions of the lungs where the gas exchange occurs. Respirable crystalline silica is too small to be seen by the unaided eye. It's less than a 15th the size of a human hair. And the smaller the size of the dust particle, the longer that it can remain suspended in the air. Now, airborne respirable crystalline silica can be inhaled and travel through the respiratory tract to the alveolar regions where it is persistent and causes damage. Now, long-term exposure can result in a series of diseases, including chronic obstructive pulmonary disease, silicosis, and lung cancer. And the effects are irreversible and there is no cure. So essentially, this slide summarises what we were talking about previously, where you've got your airborne dust cloud that's split up into the inhalable fraction, so less than the 100 microns, the respirable fraction, less than 10 microns, and then that's further divided into crystalline silica and other respirable dusts that aren't silica. So essentially, how much is too much? As for many other hazardous agents, there is a workplace exposure standard for respirable crystalline silica. Now, this slide shows an Australian 5-cent piece. It's about, should have had one to hold up and show you, but it's about 20 centimetres in diameter, so it's only about that wide. Up until last year, the 8-hour time-weighted average workplace exposure standard for respirable crystalline silica in Australia was 0.1 micrograms per cubic metre. Now, the blob to the right of the coin is approximately, or it's supposed to represent something in the order of about 0.1 milligrams of dust, which is about the size of a match head. And for longer shifts, for extended work shifts, the workplace exposure standard is reduced accordingly to account for the longer period of exposure. Now, recently in Australia, the 8-hour time-weighted workplace exposure standard was decreased to 0.05 milligrams per cubic metre. And this is an extremely low exposure standard for a very common hazard, and one that's particularly prevalent in the construction industry. Now, my view on I for the life of me don't understand why they reduced the exposure standard. It was and this is my opinion. There's a lot of people who agree with me, but it is my opinion that it was a politically motivated move because we had severe problem of coal workers' pneumoconiosis that had reappeared in Queensland, and we had the engineered stone silicosis caused by the engineered stone industry. And as a result of that, somebody said, well, we have to do something, we'll do something, we'll reduce the exposure standard. Whereas if we'd been controlling exposures at the exposure standard, then I don't believe that we would have seen the re-emergence of acute silicosis in Australia. Now, I'm sorry, I don't actually, look, I didn't get enough time to do a bit of research on this, and perhaps somebody may care to comment and answer the question, but I don't know what the workplace exposure standard for RCS is in Indonesia. Elsa, would you care to comment, or Mila?
Yeah, I think the government referred to the ACGI HCLV field, so it's right. 0.025. Yeah.
Look, we'll talk about the analysis later, but the real problem with having exposure standards set at such low levels is that the analytical techniques haven't caught up with it, and we can't actually analyse at these extremely, the level of detection, or the detection limit for the analytical instrumentation we use is at levels that are above these exposure standards. It's really, really difficult to do. I can't remember why I put that slide in now. Look, yeah, I suppose, all right, we have respirable crystalline silica. Alpha quartz is the most prevalent material that you'll come across in the construction industry. Less so cristobalite, although it is present in engineered stone, but I've greyed out tritonite as it is very unlikely that you'll ever come across it. Now, to estimate the exposure to respirable crystalline silica, breathing zone air samples are collected using a size selective sampler. There are various respirable dust size selective samplers available, and they're generally referred to as cyclones, as they operate by employing cyclonic action to separate particles according to their aerodynamic diameters. Now, pardon me, the cyclone selected should be capable of sampling of airborne dust which meets the sampling efficiency curve for respirable dust, which is the ISO ACGIH respirable fraction curve. Now, cyclones must be operated within very narrow tolerances of their specified flow rates in order to collect respirable fractions of the dust cloud in accordance with the curve. In Australia, the sampling for respirable dust is formed in accordance with the Australian standard AS 2985 workplace atmospheres method for sampling and gravimetric determination of respirable dust. And that's really equivalent to both all of the OSHA, the NIOSH and the Health and Safety Executive methods. And I apologise for references not specific to Indonesia, but as we had to change the topic a couple of days ago, it didn't leave me sufficient time to do research about or even speak with Mila or Elsha about the situation in Indonesia. However, I'm sure that the Indonesian Industrial Hygiene Association will be able to fill in any gaps in my presentation. Now, this slide has been provided by a colleague of mine, a colleague well known to the Indonesian Industrial Hygiene Association. That's Mr. Brian Eva. Who incidentally sent his best wishes as well when I asked if I could use this slide. Now, it's been included to demonstrate the need to seek advice and develop the necessary skills before undertaking any occupational hygiene exposure measurements. Now, this slide was posted on social media to promote the skills of one particular occupational hygienist conducting exposure measurements. Now, primarily, the sampler has been located incorrectly. Rather than it's actually been sitting in the rear of the cabin, attached to a fire extinguisher. To assess the operator's exposure to respirable crystalline silica, which it was purporting to do, the cyclone sampling head needed to be mounted on the operator in his breathing zone, so that's on his collar or lapel. And most disastrously, the sampling pump had been incorrectly connected to the cyclone. Rather than being connected as shown, it was connected, and it's not quite clear from the photograph, but it's been connected to either the grit pot or to the cyclone inlet. But anyway, the result is that the sample was incorrectly collected and should have been voided. Now, the lesson here is if you're going to use a consultant, get an experienced and qualified consultant to conduct your exposure assessments. And if you are in training for a career in occupational hygiene, then get a good mentor to assist you to not make disastrous mistakes like this one. It's important that only filters from sampling devices suitable for collecting respirable dust are analysed for respirable quartz. 7-hole samplers and IOM samplers are not suitable for collection of respirable dust samples for quartz analysis. And it's also noted that the exposure standards for the RCS polymorphs are set for respirable size samplers only and respirable size particles only. And these particular types of samplers do not collect respirable dust. They collect the inspirable fraction. Additionally, if by chance there is dust on both sides of the filter or on the underside of the filter, the sample needs to be rejected. Apart from the situation that we outlined in the previous slide, this can occur if the tubing becomes detached from the cyclone and the worker inadvertently reattaches it to the cyclone inlet. There are two primary techniques for analysis of sample filters. The first is Fourier transform infrared spectroscopy, and the second is X-ray diffraction. Now, infrared spectroscopy exploits the property that molecules, in our case crystals, absorb frequencies that are characteristic of their structure. These absorptions occur at resonant frequencies that are associated with stretching or bending of chemical bonds between atoms. The infrared spectrum of a sample is recorded by passing a beam of infrared light through the sample. When the frequency of the infrared beam is the same as the vibrational frequency of a bond or a collection of bonds, they vibrate and absorb energy, and so you get absorption of the ray. Examination of transmitted infrared light reveals how much energy was absorbed and at what frequency or wavelength it was absorbed. Now, the absorption frequencies are characteristic to specific molecules or crystals. The amount of infrared light absorbed is proportional to the amount of material present, so that we can use it as a quantitative assessment method. The most significant failing for Fourier transform infrared is that it can't actually distinguish between the silica polymorphs, and it also suffers from interferences from other materials commonly found in the construction industry that are also present on the filter. X-ray diffraction is used to study the structure, composition, and chemical and physical properties of crystals, and it can also be used to determine the amount of a crystalline material that's present. The structure of irradiated crystalline materials causes the beam of the incident X-ray to be diffracted in specific directions. Now, by measuring the angles and the intensity of the diffracted beams, a three-dimensional picture of the density of the electrons within the crystal structure can be obtained, and that is specific to the crystal under consideration. The relative intensities of the diffracted X-rays can also be used to determine the amount of material that's present. Now, X-ray diffraction suffers less from interfering materials than does than infrared, but its most significant advantage is it can disspeciate between the various crystalline silica polymorphs. And if you suspect that both quartz and cristobalite polymorphs may be present, then XRD has to be used. FTIR will give you incorrect results. So this table is taken from the source of it was Safe Work Australia, and it gives you an indication of the different types of rock and rock products that contain silica and the quantity, or crystalline silica and the quantities present. So, for granite, you've got 25 to 40%. I've heard of and I've seen different numbers quoted, but this is what's quoted by the Australian regulator. Sandstone, they're talking 67%. That's a very precise figure. I've heard anything between 50 and 90. And then you've got engineered stones and other composites that contain greater than 90% crystalline silica and a high percentage of cristobalite as well. And then concretes, aggregates, and mortars. It's varying depending on the amount of sand content present. We'll talk a little bit about the Sydney Metro and M5 tunnels. Sydney is essentially underlain by Hawkesbury sandstone that contains a very high percentage of crystalline silica, and the tunnel boring machines have been cutting through this silica for the last 4 years, I think it is. The Melbourne Metro system, which is the extension of the train system that goes straight under the centre of the city of Melbourne, is in the process now of, it's about 50% of the way through its work, and it's actually cutting through what they refer to as the Melbourne Formation, which is a shale silt formation that contains a relatively high percentage of crystalline silica too. Not as high as Hawkesbury sandstone, but it is still relatively high. So we've got a few pictures to show you. This is a road header in the Sydney Metro system. This rotates. Actually, I'll show you that it's better in the next slide. You can see that the cutting head rotates and cuts through the stone or the clay or whatever it might be that's ahead of it. Earthworks, transferring rock and spoil and other materials and sand into trucks for transport. It's the source of silica. Shotcreting, where you're spraying concrete onto other surfaces, and even though it's done as a wet process, has the ability to release quite significant concentrations of crystalline silica. You can see this bloke, he's cutting concrete bricks. There is no ventilation, no exhaust ventilation and no wet work, and he's generating quite significantly high concentrations of crystalline silica, or dust rather, which will be high in crystalline silica. There is a grinding of concrete surfaces. This bloke's grinding down a section of footpath, whereas the heights of the footpath the footpath has moved so that the heights are different. This fella's doing concrete cutting, dry concrete cutting. You'll notice no respirator and also no hearing protection. The laying of brick paving can also release significant levels, or probably not, certainly not as high as the other operations, but it can release respirable crystalline silica. And the cutting of engineered stone has really been a tragedy in Australia, because the engineered stone industry employs generally migrant workers, and there was little consideration given to the high levels of crystalline silica in the actual engineered stone, as it can be up to 90%. And the cutting and grinding and polishing of it releases quite significant quantities of RCS, and that has resulted in a significant outbreak in Australia amongst these trades of acute silicosis. And as I said before, it has tragically led to the premature deaths. And when I say premature, I mean very premature. You know, men in their 20s, 30s and 40s have died as a result of this exposure. So what are we going to do about controlling exposure to RCS? So the controlling exposure essentially should focus on minimising dust generation through the use of dust suppression or on-tool exhaust ventilation. Now, can utilise wet cutting or water or wetting down of the material. If you're going to use water, it's important to clean up after using wet techniques to ensure that the residues containing RCF are not left on the ground to dry out and then be disturbed and become airborne later, leading to exposure of unsuspecting people. Now, controls can include both systematic and individual options. Systematic controls focus on control at sources or of suppression of dust. Individual controls are those implemented on a personal basis by the worker. Now, keeping the work area clean is important, and always avoid dry sweeping, as this generates significant levels of airborne dust. And if it's present with silica, significant levels of RCS exposure can occur. Wet sweeping, washing down or vacuum cleaning methods should be favoured over dry sweeping. And if you're going to use a vacuum cleaner, then it needs to be fitted with a high efficiency particulate air exhaust filter. The cabins of heavy plant and equipment should be sealed and ventilated with filtered air to prevent the ingress of dust and RCS. Now, it's inevitable that mud and dirt will be walked into equipment cabins, and consequently the cabins need to be cleaned on a regular basis to avoid the mud drying out and then being disturbed and becoming airborne. When higher order controls are not available or do not provide an adequate level of protection, then we resort to the use of respiratory protective equipment. It's a final resort, if you remember back to the hierarchy of controls. We'll talk about that in a bit more in a minute. Often on construction projects, the use of respiratory protective equipment is necessary, as the higher order controls are either not available or don't provide or are not sufficiently protective. So as this side shows, please avoid dry sweeping and clean up mud before it dries. Now, I've got a couple of short film clips and I hope these work all right, but we'll see what happens. This one shows, I took this the other day actually, walking down through the centre of Melbourne, and it shows the guy, these are not bricks, they're actually tiles that are glued onto the outside of these concrete columns, and he's about to start cutting some here. So I hope you can see, I hope it works. Now you can see that's actually quite a noisy process. He's using an angle grinder, he's using it dry. He's not wearing a respirator and he's not wearing any hearing protection, and the people walking down the street are getting showered with dust that contains crystalline silica as well. There's another shot in the centre of Melbourne that I took about 3 weeks ago when I was walking down the street, and this is a machine that is scabbling the surface of the road in preparation for the laying of a new bitumen surface. Now this one was taken in, I think this was actually taken in Bali last year, where I observed this guy working. Now, I don't know how well those film clips worked over the internet, but you can see that all three of them, I hope you could see that there were quite significant quantities of dust being generated, and they were being generated from mechanical actions on materials that contain relatively high levels of crystalline silica. So you would expect or anticipate that the levels of respirable crystalline silica being generated were quite significant. In addition to the dust being generated, the tool in this case is not fitted with any guard. So if he has an accident, he could slice a finger off. The gentleman's not wearing a respirator. I don't know if you noticed at the outset when it focused on his head, he has no hearing protection on either. So now the hierarchy of controls in descending order is right now is elimination, substitution, engineering controls, administrative controls, and then essentially as a last resort, the use of personal protective equipment. Now, on construction projects, the use of respiratory protective equipment is often necessary or generally necessary, as higher order controls are either not available or they're not sufficiently protective. Now, for respiratory protective equipment to be effective, it needs to be use the appropriate respirator for starters, for the type of hazard. It needs to be worn at all times, and it needs to be worn correctly. Now, if respirators are, pardon me, if respirators are not correctly fitted and worn, they will be ineffective in protecting against the hazard. For airborne dusts in the construction industry, Class P2 respirators are generally recommended. Now, the respirators can either be a reusable type or a disposable type, depending on the level of protection that's required. Tight-fitting respirators rely on a good seal between the skin on the face and the respirator that's in contact with the skin. That requires the subject to be clean shaven. To test the efficiency of the respirator, the subject should be fit tested annually, and that's what we're showing here. This is a qualitative fit test, not quantitative in this case. Now, as much as anything, the confirmatory test or the fit test shows the subject how important it is to be clean shaven and how important it is to correctly fit the respirator. Pardon me. Now, the importance, well, this slide essentially shows the importance of good seal between the face and the respirator. Now, this here is actually a human hair. It's actually a piece of facial hair with these particles here are actually silica dust sitting on it, respirable crystalline silica sitting on the facial hair. And what we're attempting to show here, incidentally, this is a scanning electron micrograph. What we're essentially attempting to show here is the facial skin stubble, 150 microns, where the respirator is the seal between the facial skin and the respirator is being interfered with by the stubble, which allows a leak path for crystalline silica or air contaminated with crystalline silica to pass through and into the wearer's inside the respirator and be inhaled by the wearer. So this is sort of a bit of a summary page of the previous section. So controlling wet cutting, on-tool local extraction ventilation, avoid dry sweeping, better to use wet sweeping or vacuuming techniques, the use of fine mist sprays to wet things down when materials are being disturbed, respirator fit testing to ensure that you're getting adequate protection from your respirator, but also to teach the subject the importance of being clean shaven and correctly fitting the respirator, and then a clean shaven policy. And I hunted this. I couldn't find a better subject to use here. Actually, this is an actor in America. But what I wanted to show here is that the clean shaven skin, you will get a good seal between for a tight fitting respirator, you'll get a good seal between the respirator and the skin. And even a small amount of stubble, like 2 days worth of growth, interferes with the seal and can result in exposure through air being drawn in past the seal. Now, I wanted to include this one, and I shot this in China in beginning of 2019, actually, at a woodworking facility where they create the most amazing sculptures, and they finish them off by actually sandblasting them, and it is sand. And even though the guy's got an air wash hood on, and unfortunately I didn't think at the time to show what is happening to the dust that's being generated, because he's in a separate area and he's blasting away at the surface of these things to finish them off, but the dust is coming out of the area and wafting straight back into the area where the unprotected people are working. So, that's about, I'm about 30 metres away, and you can hear that it's really quite loud, and that was a really loud process. But it was generating really significant quantities of dust that were blowing out from where he was working and straight back into an area where unprotected people were working. Now, I thought we might spend just a minute talking about the UK Breathe Freely program. Now, the UK Breathe Freely is aimed at reducing occupational lung disease, which causes a significant debilitating ill health and an estimated 13,000 deaths per year in the UK. Now, the BOH initiative was launched in 2015 and has been highly successful in providing education and awareness of safe work practices and resources to control exposures. The resources are available online to both workers and employees, and anybody globally can log on and download the material. The BOH has very, very generously also permitted other countries like AIOH and NZOHS to utilise their resources. So it may be something that MIIHA may want to consider as well. At the recent BOHS conference, which Mila tells me she was logged on to the other night, they quoted 3,500 cancer deaths per year in the UK and 5,500 cancer registrations in the UK, both of which were related to occupation. Now, occupational disease is a significant problem, and death from occupational diseases is about 10 times that the death rate from accidents associated with work. We'll talk a little bit about noise. Most people don't realise that noise-induced hearing loss is the most compensable of all the occupational diseases. And again, from the BOHS conference the other night, they quoted the rates of noise-induced hearing loss to be twice that of all other occupational diseases combined, and it costs the UK economy more than £400 million annually. That's about 7.8 trillion rupiah. Noise and noise-induced hearing loss in the construction industry are significant problems, and the typical sources of noise include heavy plant moving materials around, those road headers and other equipment, trucks and loaders moving equipment, hammering to either break concrete or to break rock where they can't cut through it other way. They hammer away at it. Shotcreting, because it's using compressed air, is very, very noisy. Hand tools are it can be very noisy instruments, and the use of compressed air, if it's not fitted with exhaust. Oh, what's the wording I'm looking for? I've lost my train of thought. But the exhaust, it's not fitted with a silencer is the word I was trying to think of, an exhaust silencer. And I don't know about in Indonesia, but on construction sites in Australia, they like to play music and have the radio going and boombox type things, and they turn them up so loud so that they can be heard over all the other noise sources that it can be really quite noisy indeed. Now, The frequencies damaged by noise-induced hearing loss are those frequencies that we require for verbal communications. And consequently, the effects are progressive and chronic. So you may get a temporary threshold, acute thing like a temporary threshold shift, but the effects are felt over a long term. They're chronic, and because they're chronic, you don't realise that it's happening until such time that your hearing has been damaged and you know, sorry, I can't hear you. And then as you get to my age, the grandchildren aren't interested in communicating with you anymore because you can't hear them and you don't respond. So they just, oh, grandpa, he's deaf, we won't worry about him. So this can be a real problem in communicating with people that have got noise-induced hearing loss. Now, it's important also to note that some of these sources also contribute to vibration exposure. Now, noise sources can be both task-based, so that's tools used by the worker, or constant and varying, so that's background noise, boom boxes, etc. Now, noise surveys, so that's a point and shoot with the sound level meter, is useful to identify noise sources and delineate hearing protection zones. But noise dosimetry is required to assess personal noise exposure. And my apologies again, but I've only got the Australian limits for occupational noise. Now, this gentleman is wearing a noise dosimeter, microphone sitting on top of his shoulder adjacent to his ear, so it's measuring his personal exposure to noise. Now, it should be noted, however, that you can have different noise doses to different ears depending on what you're doing, whether you're a right-handed person using a drill on the right or left-handed or whatever. So you can get differences in exposure to the different ears. But for in Australia, the linear equivalent 8-hour time-weighted average is 85 dBA, and it's obviously lower for longer shift durations. And the LC peak is 140 dB instantaneous. Now, Elsha or Mila, look, I'm sorry that I haven't quoted the Indonesian ones, but are they the same or similar?
Yeah, we have the same daily limit.
Well, that was fortuitous, wasn't it? Thank you. Now, again, using the hierarchy of controls to control noise and noise exposure on construction sites is problematic, as eliminating or controlling or reducing noise at source is generally impossible. Commonly, hearing protective devices used to address constant and task-based noise on construction sites. My observation that on construction sites here, that most workers have a very cavalier attitude to the use of personal protective equipment, in particular hearing protective devices, and consequently hearing protection programs in Australia that rely on the use of hearing protective devices have met with very, very mixed success. I just wanted to talk about correct and incorrect fitting of earplugs. Most people on construction sites haven't been shown how to correctly fit the things, and they just try and shove it straight in their ear canal, and they're poking out like this, and they're offering very, very little protection. They need to be carefully rolled down, the pinner pulled backwards and then shoved into the ear so that they sit right inside the ear canal, where they swell up and seal off the ear canal. Actually, we'll just look. I'm just noting the time, and I've gone over time, or I'm about to go over time. So we'll quickly talk about diesel emissions. Most heavy machinery used on construction sites is powered by compression ignition engines, or referred to as diesel engines. Now, diesel exhaust has both gaseous phases and diesel particulate matter. The gaseous phases can include things like carbon monoxide, unburned fuel, and oxides of nitrogen and lesser oxides of sulfur compounds. Diesel particulate matter is comprised the burnt component of it, and we measure it, but with elemental carbon. The exposure standard, it's actually a guideline. It's not a fixed standard as such, but the guideline is 0.1 milligrams per cubic metre measured as elemental carbon. So there are a number of controls. The most important thing is engine maintenance. The engine needs to be tuned so that it reduces the amount of diesel emission. And the exhausts can be fitted with scrubbers or filters. And then in construction sites, we're like on the Melbourne Underground at the moment, which is where I'm working at the moment, providing hygiene advice there. The only thing that we can really do is provide significantly increased ventilation systems and brattice curtains to line off sections of the tunnel where we're working. Exhaust both extraction and supply dilution ventilation as well. And then, as a final resort, personal protective equipment. Now, personal protective equipment will protect against diesel particulate matter, but it does not protect against nitrogen dioxide. In fact, there are no filters that will protect against nitrogen dioxide. So the only thing that we can do there is provide sufficient ventilation to dilute the material down to the lowest level that we can get it to. I just thought asbestos is one of those things that you encounter in older buildings all the time. It was used very, very extensively up until, well, in some areas, some places it's still being used. It's not used in Australia anymore, but there are thousands of tonnes of asbestos-containing product that are present in Australian buildings. Now, there's a list of the general properties of asbestos. Because it had a very big range of very useful properties. It was used in a myriad of products, many thousands of products. So the typical uses in the construction industry are, as cementitious construction materials. It was used extensively in fireproofing, thermal and acoustic insulation. It was woven into fabrics and ropes. It was used as binders or fillers and extenders in other products. It's used on friction materials, and because of its high electrical resistance, its resistance to fire, it was used in electrical equipment. And there have been many, many thousands of products that have been manufactured using asbestos. It comes into two different types of products. They're referred to as friable and non-friable. Friable materials, those things that it's actually a definition, and it's a very poor definition, but what it is, it can be crushed down to powder between your fingers when it's dry. But essentially what it means is that it's a material that is easily disturbed, and when it is disturbed can liberate quite significant quantities of airborne respirable fibres. Friable materials, on the other hand, the material, there's generally less asbestos in the material. It's bonded into the matrix, and it requires significant disturbance to liberate airborne fibres. And if you think about things like asbestos cement sheet, the only way that you can liberate fibres from that is by disrupting the matrix by running a power saw through it or something like that. So on the left, you've got a non-friable fragments of asbestos cement, and on the right, you've got friable asbestos insulation. So the health effects resulting from exposure to asbestos from the inhalation of respirable fibres. And the respirable size range for asbestos, for fibres, not just asbestos, the respirable size range for fibres is differently to things, to other dusts. that are spherical in nature. Because of the nature of asbestos materials, because of the nature of asbestos, when the fibres are ruptured, they split along the length of the fibre that produce long rectilinear fibres that are very, very fine in diameter. So respirable size range is defined as those fibres that are greater than 5 microns in length, less than 3 microns in diameter, and have a length to width ratio that's greater than 3 to 1. And it's fibres in that size range that possess the aerodynamic characteristics that allow them to penetrate down to the gas exchange or the alveolar regions of the lungs. Now I've remembered. So we've got this gentleman wearing personal protective equipment, a respirator, glasses. He hasn't got any hearing protection on, so I hope he's not doing anything noisy, and a hard hat. So these are typically the types of personal protective equipment that you will be utilising on a construction site. I was going to talk a little bit about heat stress, but I've now gone significantly over time. I was actually told 45 minutes, and that was extended to an hour. So we could probably call it quits at that point. And if you've got any questions, and look, I can always come back at another time and talk about heat stress or anything else that you'd like me to talk about as well. So thank you very much for the opportunity, and happy to take any questions.
Thank you, Phil, for your great presentation. We have few questions here. I will read the question, and for the others, if you want to ask directly to Phil, just raise your hand.
So if I turn this presentation off, how do I do that? Escape. And then I can, okay. Sorry, I'm just trying to get,
Okay, first question from Pak Joko. I think it's about the analytical method from OHA. Do you familiar with OHA analytical method, Phil? The question is how to calculate combination PEL for silica using OHA ID 142 as a reference. Do you familiar with the OHA analytical method?
Look, I'm not. If you look, that doesn't mean that look. What I will do is, for those questions that, and I apologise if I can't answer them straight up. Those questions that I am not able to answer straight up, if you could put them in a list and email them to me, then I would be very happy to give to do the research and provide an answer, in a week or two.
Okay, I will send you the question, but I think the OHA 142 actually put the calculation method on the document. So I will check with Pak Joko again the specific question for you.
Yeah, look, if you can send it through, and I'll have a look at it, and then I'll respond as soon as I can. Okay.
The second question comes from Mbak Maria, yeah. So she actually asking about the control measure for the blasting activity in the confined space. So the current control measure that she did in her workplace is that the operator of blasting, they wear the supplied air respirator, while the other worker who works surrounding the area only wear the half mask respirator. The other control measure is by providing adequate ventilation into the confined space. So do you think it is adequate or sufficient control measure?
Look, that's a very open-ended question. It's a little hard to answer. We're involved in similar type of work in both the Melbourne Metro system and on the M5 East although the Sydney Metro work's been drawing to a close. But essentially, what we were doing is providing on-tool extraction ventilation where it was possible, but that's often not possible on large construction equipment. So we were providing extraction ventilation to the surface through a scrubber, and then supplied air ventilation down to the work face as close as we could get it, and then separating those areas where that type of work, those dust generating activities were occurring from the other locations by the installation of brattice curtains to isolate the area where the high dust load was. And then the workers were either working inside cabins that were fitted with filtered supplied air or an airtight cabin fitted with filtered supplied air, or they were wearing respiratory protective equipment adequate for the level of exposure. In some cases, airline respirators, in other cases, PAPRs. So I hope that answers the question. If you need further detail, as I said, I'm happy to write back. Okay.
Okay. Thank you, Phil. I think we have Bapak Frans Suhadak ya. Pak Frans, silakan kalau mau bertanya langsung.
Suara saya bisa didengar ya?
Ya, bisa Pak.
Pak Phil, good morning Pak. Maybe afternoon in Australia. I'm Frans from Jakarta, Pak, and I'm working in a group from some Australian company in Indonesia. And it's very interesting that occupational health and hygiene in Australia is quite strict. That I see that government is reinforce the rules, regulations is quite strictly in there. This is quite different with Indonesia. That if I see that some of your company in Australia using professional providers to manage their occupational health and safety. Maybe this is the differences between Australia and Indonesia if we're talking about the implementation. I'm not expert in occupational health and hygiene, but I see that a lot of differences between the Australia and Indonesia if talking about the implementation.
Pertanyaannya, Pak?
Yeah, the challenge.
Oh, sorry.
The challenge here is when we try to implement what is look like Australian standard in here, it's quite difficult because not much reinforced from government. This is from my point of view, yeah. But feel free for discuss.
Look, the setup of occupational health and safety, of which occupational hygiene is a subset in Australia, has a unique set of problems, as it does in Indonesia. I don't know how many thousand islands comprise Indonesia, but I know that there are many, and there are a lot of very small businesses. Australia, although it is one big island, or off the Tasmania, and they'll kill me, one very large island with a smaller island off the bottom, we have similar problems because of the disparate locations across a very large landmass where people work. We also have an added complication insofar that Australia comprises 7 separate states which are independent and autonomous. So it is essentially like 7 little countries federated under one Commonwealth. Each of the state systems have their own laws for a whole variety of things, but in particular, environment and workplace health and safety. And consequently, they're all different. And some are better than others. Some have better components than others. And look, I've been working in this industry now for a little under 40 years. And we've been trying to get harmonised legislation across Australia in all of that time, and it has still not been achieved. And I think I'll be long in the grave before it is. So we have our own problems, and we've got, you know, sort of the one thing that we don't have in Australia anymore because of the cost of employing people is that most of our manufacturing industry has moved offshore. So that the industries that we have here at the moment are heavy industry associated with construction and infrastructure development and mining. Yes, Australia has been very fortunate to be very rich in natural resources, and so we've got a very, very large mining industry operating as well. But trying to develop and run health and safety programs across very disparate locations in a land like this has its own problems. But the regulators in Australia, I was about to say they're very strong, but they're very strong in some areas and not so strong in others. So you see some really quite significant issues that are occurring. In fact, I think I've got it in, just bear with me a minute. I think it's, oh, I do too. Look at that. Hang on, and I'll try and share this film clip with you just to show you some of the problems that we do have here. I assume that when I shared those clips before, that they actually came across reasonably well, did they?
Yeah.
This was given to me by a colleague very recently, this film, and it shows a mine in WA where and it's been like this for years, where they're having problems with one of the crushers and it's never been resolved. Mind you, I've just realised I can't work out how to start the video. Oh, here we go, here we go. You can see the dust build up on the front of his lens already and all that, and that's a dust track, and that is maxed out at 150 micrograms per cubic metre on respirable dust. 150 micrograms per cubic metre. That has blown right across the mine site and down into the valley below. Huge amount of dust. Disgraceful. And yet the regulator has done nothing about it. They would pretend that they're not aware. I'll stop that there. Stop screen sharing. So, yeah. So look, we have quite significant problems here also. Some of which I would venture to say there's probably some commonality between problems here and administration and implementation problems. Probably the nature of the problems are different, but the implementation and control is there's probably some similarity between Australia and New Zealand, but sorry, not New Zealand, Indonesia, I beg your pardon. But there's also, you know, there'll be a myriad of problems that you will have there that we will not see here because of the different nature of the industries that you have there.
Ya.
Thanks Philip. Thanks Philip.
Mungkin kita bisa lihat ya, di negara maju aja masih ada masalah perbedaan atau gap ya antara peraturan dan implementasi. Jadi kita di sini memang challenge-nya masih lebih besar lagi. Mudah-mudahan teman-teman tetap persisten, karena kalau kita mengandalkan regulator ya nggak akan banyak ada kemajuan gitu. Jadi memang praktisi HSE atau IIHA ini memang harus jadi agen perubahan lah, bisa seperti itu. Baik, oke, Phil, next question from Pak Insan. So he's asking, is there any similarities between the theory and actual if we use the ear protection in work area? I think he's asking about the effective noise reduction rate between the theoretical and the actual. For example, in the for ear plug, in the ear plug package, they write the NRR is 25 dB. So what is the effective NRR for the actual in the workplace?
The difference between, so what you're asking is the difference between the theoretical protection and what's actually provided in practice. Yes.
Yeah.
Well, I suppose it depends on the class of hearing protector worn, and they don't actually provide the attenuation factor, but you can assume it. You know, like for class 1, good to up to 90 dBA. Class 2, 90 to 95. So you can assume that the attenuation has got to be better than 10 dB, and then all the way up to class 5, which is sort of 105 to 110 dBA. So you've got to assume that the attenuation has got to be better than 25 dB. However, for all of those, they assume that the earplug is correctly fitted in and fully into the ear canal and is fully blocking up the ear canal. And from what I've seen in Australian workplaces, to have the earplugs correctly fitted is more rare than it is to have them not fitted correctly, where they've just shoved them in the outside and they're poking out like Shrek's ears, So we are on a big campaign here to try and educate people to correctly fit the earplugs. Now, I appreciate that doesn't specifically answer the question, but if you send that across to me, I will speak with our acoustician and ask him to provide a better and fuller answer.
Okay, if I may, Phil, I will add some comment in bahasa Indonesia ya.
Yes.
Ya, mungkin Pak Insan kalau di kita lebih familiar dengan pendekatan, misalnya dari OSHA dia ada kayak pendekatan kalkulasi ya, yang dipercaya dari NRR yang ada di kemasan earplug atau earmuff itu kita kurangin 7 dulu, baru nanti yang kita percaya 50%-nya. Itu pendekatan simpelnya. Nah, faktor-faktor yang mempengaruhi efektivitasnya tadi disampaikan Pak Philip. Salah satunya yang terpenting adalah apakah earplug atau earmuff itu digunakan dengan baik gitu. Karena sering sekali tuh, terutama kayak earplug, kita pakainya tuh asal masuk aja, tapi benar-benar nggak diinsert benar-benar dalam lubang telinga. Jadi asal nempel. Pokoknya dari jauh kelihatan oleh supervisornya pakai earplug gitu. Nah, itu mungkin yang perlu dilihat lebih lanjut. Sementara mungkin itu Pak, nanti kalau pertanyaan lebih detail lagi bisa disampaikan atau mungkin nanti kita ada sesi khusus untuk noise ya, kebisingan. Baik, next question from Dita. To remove or dismantle material that containing asbestos safely. I think this one is one of your expertise.
I've done it for a long time. Yeah, so the question is how to, did you say, or
how to remove or dismantle ACM?
All right. Well, look, that depends on the type of asbestos-containing material that it is, whether it is a bonded product or a friable product. Bonded products are far more robust than friable materials, and consequently they don't release asbestos fibres as easily, so that the controls for their removal are a lot less stringent than they are for friable materials. So friable materials would include things like, sprayed products, pipe lagging, and boiler insulation and that type of materials. They require far more stringent controls. I can certainly send some information on that, but essentially what you would do is build a fully sealed, plastic-lined and dust-tight enclosure around the materials to be removed, and then you fit that enclosure with an extraction ventilation fan that sucks air out of it through a particulate, high-efficiency particulate air filter and ventilates it to the atmosphere. That has the effect of, because it's a dust-tight, and you can't talk about airtight, it's a dust-tight enclosure. By sucking air out of it, lowers the pressure inside the enclosure with respect to the outside. So if there is a leak, you get the net effect is that clean air is leaking in rather than contaminated air leaking out. And then people that work inside there wear appropriate levels of PPE. In that case, it would probably be an airline respirator or a PAPR. They enter the enclosure via a decontamination unit. They do the work wet that they need to do, and then on leaving, they decontaminate and wash themselves off, and then take their respirator off. That is a very, very rough description on how it's done. But I'm happy, again, if you wish to send a question across, I'm happy to try and provide further detail on that if necessary.
Okay. Phil, question. In Australia, do you have any specific regulation that determine the competency level for those dealing with the asbestos removal?
Yes, there are. Look, again, it's a little disorganised in some ways. The regulator would dispute that, of course, but there are people that do the asbestos removal themselves, and then there's people like myself that work as an occupational hygiene consultant. For the removal of asbestos, there is a requirement for the contractor to be licensed. There are two levels of licensing. There are Class A licenses, which are required by a contractor engaged in the removal of friable asbestos-containing materials, and then there is a Class B contractor that is required, and that's required for the removal of bonded materials. Actually, Class A can do either friable or bonded, but Class B can do bonded only. Then for consultants, and this is actually where there is a degree of commonality between the states. It's very rare, but it is in this case. So the licensing requirements for asbestos removal contractors, but also there is a license required for consultants working and providing air monitoring services or clearance certificates for friable asbestos removal operations, and they are required to have what's called, or to be what is called, a licensed asbestos assessor.
Okay. I think a general comment for Mbak Dita ya. Mbak Dita, mungkin pekerjaan terkait asbestos containing material, kita harus benar-benar melakukan risk assessment yang komprehensif ya, karena asbes ini dia tuh ibaratnya macan dalam kandang. Artinya kalau dia dalam kondisi baik sebenarnya tidak berbahaya, tapi kalau kondisi baik tapi kita malah ganggu, itu malah menghasilkan debu yang berbahaya buat kita. Jadi sebaiknya kumpulkan banyak-banyak informasi untuk melakukan risk assessment secara komprehensif. Banyak informasi, kalau mau ke website ETC UK juga banyak, Mbak Dita, bisa dilihat dari sana. Karena nanti banyak sekali yang perlu diperhatikan, mulai dari tadi Pak Philip bilang kompetensi orangnya, kemudian air monitoringnya, APD, dan seterusnya. Okay, next question. From Pak Aditya. if we do SEM removal, the asbestos content in the material is 5%. Sorry, is 5% according to the AMSDS. And then he did air sampling, and the result is 0.02 fiber per cc. Is this result interpreted as pure asbestos or total fiber, which means that the result contain asbestos fibers and other mineral fibers?
All right, now, all right. Oh, sorry if you finished.
Yeah, it's finished.
Okay, all right. Look, depends on the analytical method used. The membrane filter method is an estimate of airborne asbestos fibres. You can either do the analysis by transmission electron microscopy, which is very expensive, but probably 99% of the analysis that's done in the world outside of the US is done by by phase contrast microscopy. Phase contrast microscopy looks at the size, shapes of the filter and the shapes of materials on the filter, and compares it to established size criteria, which I gave before. So it counts any shape on the filter that's longer than 5 microns, less than 3 microns in diameter, and has an aspect ratio of greater than 3 to 1. It counts that as a fibre. It does not have the ability to discern between cleavage fragments on the filter that may be from other mineral particles that may conform to that size criteria, or an asbestos fibre. The single biggest advantage that electron microscopy has over optical microscopy is that if it's fitted with a energy dispersive X-ray analyzer, it can analyse the individual fibres that you look at and look at the chemical composition of it, and look at that to see whether it's consistent with one of the asbestos fibre types or not. So the shortfall of phase contrast microscopy is that it can't do that, and so that you just have to assume that whatever you count on the filter that conforms to the size criteria, the geometric size criteria, is asbestos. For that reason, you need to be very careful where you collect your sample, that if it's going to be collected in an area where there could very well be significant input or contamination, if you want to put it, from other types of fibrous products, then you need to be very careful about how you're going to sample, where you're going to sample, and what analytical technique you're going to use.
Okay, thank you Pak Phil. Pak Aditya, mudah-mudahan dapat poinnya ya Pak ya. Jadi salah satu faktor bagaimana cara interpretasinya juga tergantung dari analytical method yang digunakan. Tadi dicontohkan kalau pakai phase contrast mikroskopi itu hanya total fibernya aja. Tidak bisa detail chemicalnya itu apa, kecuali pakai elektron mikroskopi. Okay, next question. What are the anticipated health hazards when we demolish a boiler which built in 1972?
Boiler built in 1972. What was it fired by? Is it gas or oil or coal? Let's just talk about it generally then. Okay. Yeah. I'm assuming that it's a large boiler. Let's say it's a large coal-fired boiler in a power station or something like that. I've done a few of those. There are a number of things. You're certainly going to encounter asbestos products if something that was built in 1970. The expansion, it depends on the construction of the boiler. I'm assuming that it's a high-pressure boiler and not a tube, a low-pressure tube boiler. Generally, they have a firebox that has it's got a water wall box where the tubes are built into the wall and they're heated on the inside. And then the gas path has fire bricks, etc. in it, and the whole thing is insulated with fire bricks. Or refractory bricks, I suppose I should call them correctly by the correct terminology. And there's likely to be asbestos insulation on that as well. The expansion joints in the refractory brick will be packed with something that is fire resistant, robust and flexible, and it's very likely going to be friable asbestos materials. The flange joints on the pipework will very likely be an asbestos jointing material. And the other thing to consider is that the fire bricks or the refractory bricks themselves will have a high percentage of crystalline silica in them. And because it's been heated up to 1000+C on the fire face, it's very likely that alpha quartz will have been converted to cristobalite. So you'll see both cristobalite, alpha quartz in the bricks and the dust that's generated. So I would think that the primary areas of concern are to try and remove all the asbestos materials that you can beforehand, and then when you're just demolishing the refractory brick material, to try and control the dust as best you can with some sort of an enclosure or brattice curtains or something like that, and then wetting the material down and putting the people in appropriate respiratory protective equipment. But yeah, I think the primary things that you'll come across that I'm just trying to think will be asbestos and crystalline silica. If the boiler is still full of boiler water, if you've just shut it down, the boiler water will have hydrazine in it, which is there to stop the corrosion of the internal corrosion of the steel, and that brings about its own problems as well. But I'm assuming, well, you could probably dump the boiler water to the sewer. I don't know. Actually, I'll retract that statement because I don't know what your requirements for discharge to the sewer are in Indonesia. But there quite possibly could be other things like mercury switches and materials like that on boilers as well. So it really depends on what type of boiler it is.
Okay, thank you, Phil.
Yeah, look, I hope that answers the question. Again, if the gentleman that raised the question has, or the lady that raised the question has questions in relation to a specific type of boiler, send me some details and I might be able to add better and further particulars.
Oke, ini Mbak Darlina ya yang nanya tentang boiler. Kira-kira udah cukup atau she said it's a fire tube boiler.
So what sort of pressure were the tubes running at? Is it a high pressure boiler or low pressure?
Mbak Darlina bisa kasih informasi lebih lanjut atau high pressure?
Oh, all right. So 70+ bar then. All right. Well, look, in that case, it'll most probably be a water wall boiler, and the tubes will be the superheater tubes. So the gas path is generated in the firebox. The firebox is lined with the boiler tubes. They go up to a steam drum. They percolate down to the water drum, and the whole system moves through that. Then the steam is drawn off the steam drum and pumped through or piped through the superheater headers and the superheater tubes themselves, and then out to the field to do the work. So that's the gas path. There will be refractory bricks in that boiler that have been heated to 1000+ degrees, so that they will have converted the alpha quartz into cristobalite. So yeah, I think that the recommendations would remain unchanged. The things you're going to come across will be undoubtedly asbestos, but also respirable crystalline silica in the form of alpha quartz and cristobalite.
Okay. I think, yeah, it's quite clear. The primary hazard that should be anticipated is asbestos and RCS, yeah?
Yes.
Okay. Is there any further question? Okay. I think there is no further question, Phil.
All right. Okay then.
Okay.
Look, thank you very much for the opportunity to speak with everybody today. It has been my distinct pleasure to present to this audience, and I would love to come across. If we ever have international travel again, I would love to come across to the next conference of the Indonesian Industrial Hygiene Association and see you all there, and perhaps we can have further converse on these or other topics, or happy to talk on asbestos or whatever you'd like me to talk on. Okay.
Okay. Again, on behalf of the Indonesian IIHA Association, Phil, I would like to thank you again for providing your valuable time with us today, sharing your expertise and experience. And hopefully, as you mentioned, we have another opportunity to collaborate with you again in the future.
Yes. Okay then. Thank you very much, everybody.
Thank you so much, Phil.
All right. Cheers. Bye-bye.
Okay. Have a good weekend.
Thank you. Same to you, everybody. Thank you. Bye-bye. Bye-bye. Take care.
Thank you, Bill. Thank you, Bill. Chef. Thank you.
Bye-bye.
Semua.
Terima kasih.
Bye, everyone.